Everyday physical matter cannot occupy the same space at the same time. But when it comes to waves, for example mechanical waves or electromagnetic waves, these can occupy the same space at the same time. In fact, they can move through one another without being permanently destroyed or altered in any way. So we're on the O Physics website, and I'll put a link in the description if you want to play around with this yourself. And with this app, we're looking at two pulse waves undergoing constructive interference. So we have a slider at the top here, so we can control precisely how fast the time moves ahead. So when I slowly move this slider along, we'll see both the left and right pulse wave move towards one another. Now, I want you to guess what might happen when these two pulse waves merge together and occupy the same space. What do you think the resultant wave would look like? So we're inching time forward slowly here, and I'm going to stop at time 0.67. So at this point, we can see the two waves merge together and start to grow in the center here. So what's happening here? Well, if you look at the orange and blue dotted lines, these represent the left and right wave pulses. And now the black wave here is the sum of the left and the right pulses. So each of these grid squares has a height of 1. If we pick a random spot along our wave, say the center here, where the orange and blue wave intersect, if we then estimate its height above the equilibrium position, I'd say both these intersect at about 0.8. The resultant wave, so the black line here, is the sum value of these two heights. So the height of the blue wave and the height of the orange wave at this specific point. So what we've done here is applied the superposition principle. In other words, this is the method of summing the displacement of two or more waves that are occupying the same space. And in fact, this simulation from the O Physics website is using the superposition principle to calculate what our resultant wave should look like as we move through time. So this type of wave interference is called constructive interference. We have a superposition of two waves here in which individual displacements on the same side of the equilibrium position are added together to form the resultant wave. So if we flip one of these pulse waves into a negative position, what do you think will happen to these pulse waves when they flow into one another and occupy the same space? So again, we apply the superposition principle and add the individual displacements together at each point along the wave. So when we scroll forward to a time of t is equal to 0.74, if we were to add together the orange and blue pulse waves at every point along the x-axis, their values would sum to the resultant wave here. This type of interference is called destructive interference. In other words, a superposition of two or more waves in which individual displacements on opposite sides of the equilibrium position are added together to form the resultant wave here. Now, when both these waves occupy exactly the same position along the x-axis, they completely cancel out at this specific point in time. So when they cancel out like this is called complete destructive interference. But again, as the pulse waves move past one another, if we move the time forward a bit, they regain their original shape. And again, just to remind you, I've placed a link in the description for this simulation so you can explore it yourself and see what happens when the waves have different heights, for example, and different widths. Waves are reflected differently depending on whether the medium, like a rope for example, is attached freely to a boundary or whether it's fixed at the boundary. So we've got a rope made up of these red and green balls here, or circles, and the right hand side has been held in a fixed position. So what do you think will happen to this pulse wave as it hits the fixed boundary and it gets reflected back? So we see the pulse being inverted while keeping the same amplitude. And this happens when a wave strikes a fixed boundary. So when the pulse wave reaches the fixed clamp here, this rope or elastic string exerts an upward force on the clamp, and the clamp in turn exerts an equal and opposite reaction force on the rope. So in other words, the clamp pulls down on the rope with an equal force. So this downward force is what causes the pulse to invert when it's reflected. And this is Newton's third law in action here. So for every action, there's an equal and opposite reaction. So what we have a free boundary now, or a loose end, where the end of the string is attached to a loop and the ring is free to slide without friction. What do you think will happen to the pulse as it hits the boundary here? So the incident pulse is reflected back with the same amplitude and without being inverted. And this is because the medium is not attached to a fixed boundary. It's able to move in the y direction.